A Chinese battery company says it can now put almost an entire charge into an electric car in 6 minutes and 27 seconds. That sounds like the moment gasoline cars lose their last undeniable advantage. But there is a problem hidden inside that number. CATL did not prove that every driver can pull into a roadside station, connect a cable, recharge, pay, disconnect, and leave in 6 minutes. It reported that its third-generation Shenxing battery can move from 10% to 98% state of charge in that time under its specified conditions. That distinction matters, because if the number can be repeated inside affordable production cars using public chargers across summer heat, winter cold, and years of ownership, the argument against electric cars changes dramatically. A gasoline car can travel hundreds of miles after a short fuel stop. An electric car may be cheaper to operate and smoother to drive, but on a long journey, the driver still waits. CATL is attacking that wait directly. Its new battery reportedly reaches 80% in 3 minutes and 44 seconds. It can move from 10% to 35% in only 1 minute. CATL even claims that in temperatures of minus 30 degrees Celsius, the battery can rise from 20 to 98% in about 9 minutes. These are company-reported figures, not yet a complete independent verdict. But the most important part of the story is not the stopwatch. It is what must happen inside thousands of battery cells during those 6 minutes and what could go wrong if even one part of that process falls behind. A battery does not fill like a fuel tank. Gasoline flows through a hose and remains gasoline inside the tank. Charging a lithium-ion battery requires billions of lithium ions to leave one electrode, travel through an electrolyte, and enter microscopic storage sites inside another electrode. Imagine trying to move an entire stadium crowd through thousands of tiny corridors. Increasing the electrical current is like ordering everyone to run faster. That works only while the corridors remain open and every person can find a destination. Push too hard, and congestion begins. Inside a battery, one dangerous form of that congestion is lithium plating. Instead of entering the anode properly, lithium can collect as metallic deposits on its surface. That removes active lithium from the battery, accelerates capacity loss, and can create dangerous internal structures. This is why the 6-minute claim represents more than a powerful charger. CATL describes the new Shenxing battery as having an equivalent 10C charging capability, with a peak rate reaching 15C. 1C would theoretically charge a battery in 1 hour. 10C compresses that energy transfer towards 6 minutes. For a phone battery, that sounds impressive. For an electric car pack holding enough energy to move a heavy vehicle for hundreds of kilometers, it means forcing an enormous amount of power through electrochemical material without allowing local sections of the cell to overheat, overcharge, or become starved of lithium ions. The difficulty begins at the electrode level. Thicker electrodes can store more energy with less packaging, helping range and cost, but lithium must travel farther through them. Thin electrodes can accept charge more easily, but may reduce energy density and require more inactive material. Smaller particles can shorten the path lithium must travel. Yet changing particle size affects surface area, chemical stability, manufacturing, and durability. The electrolyte must conduct ions rapidly. The anode must accept them without plating. The cathode must release them without excessive resistance. The internal current collectors, tabs, and connections must distribute power evenly, because average temperature is not enough. A battery pack could report a safe overall temperature while individual regions inside certain cells are much hotter or colder. The colder areas may accept lithium too slowly. The hotter areas may age faster. Small differences can grow over hundreds of charging sessions, causing cells to drift apart in capacity and resistance. CATL says its answer includes reducing heat production, improving heat propagation, and controlling the process more precisely. That wording reveals an important engineering reversal. The objective is not simply to keep the battery cold. Lithium ions move too slowly when the cell is extremely cold. Aggressive charging under those conditions increases the danger of plating. The battery may first need to be warmed into a more favorable range. Then, once enormous current begins flowing, the same system must prevent that helpful warmth from becoming damaging heat. The vehicle is therefore performing a thermal balancing act. Before reaching a charger, its navigation system may identify the destination and prepare the pack. Pumps circulate coolant. Valves redirect heat. The motor, inverter, cabin system, and battery may exchange thermal energy. By the time the driver connects the cable, the battery has ideally been moved into the narrow temperature region where it can absorb power rapidly. The charging system then watches cell voltages, current, temperature, state of charge, and estimated internal conditions. If the pack becomes uneven or approaches a safety limit, the current must fall. This is one reason a charging curve matters more than a peak number. A battery might briefly touch an enormous power level and then slow dramatically. What determines the driver's waiting time is how long it can maintain high power across a wide portion of the charge. CATL's reported 10 to 80% time suggests the company is claiming more than a momentary peak. But there are still unanswered questions. What was the battery's usable capacity? What temperature was used for the headline test? How much preconditioning occurred? How often can the maximum rate be repeated? What exact charging profile protects the cells near the top of the pack? And what happens after years of real driving? CATL says capacity remains above 90% after 1,000 complete cycles. That would be significant, but cycle life numbers depend heavily on temperature, charging frequency, depth of discharge, rest periods, and the definition of the test. Independent vehicle data will matter more than a launch stage claim. Still, even perfect cycle life would solve only the first half of this problem. Because a battery capable of accepting energy this quickly is useless unless something can supply it. Consider a car adding roughly 80 kilowatt-hours in 6 minutes. Ignoring losses, that represents an average power flow of around 800 kilowatts. A larger pack or a more aggressive section of the charging curve can push the requirement toward 1 megawatt or beyond. That is not an upgraded wall socket. It is industrial-scale power arriving through a cable held beside a passenger car. The connector must survive it. The cable must be cooled. The vehicle's electronics must convert it. The station must obtain it. The local transformer must support it. And if 4 drivers arrive together, the problem does not remain 4 times as simple. So the real question is no longer whether China has built a battery that can charge in 6 minutes. It is whether China is building an entire energy system capable of making those 6 minutes real. And that is where the 6-minute battery becomes something much larger than a battery breakthrough. A charging station does not create energy. It receives electricity from the grid, converts it into the form the vehicle can accept, controls its voltage and current, removes waste heat, and delivers it through a connector that an ordinary driver can handle safely. At 1 megawatt, every part of that chain becomes difficult. Increasing voltage helps. Power equals voltage multiplied by current. So if engineers raise the vehicle's charging voltage, they can deliver the same power with less current. That matters because electrical heating rises with the square of current. Double the current, and resistive heating can become 4 times greater. But higher voltage does not make the problem disappear. The charging cabinet still needs expensive power electronics. The cable and connector still require thermal control. The vehicle still needs compatible contactors, insulation, sensors, bus bars, and battery management software. And the station still needs access to enormous grid power. Imagine 4 vehicles arriving at a highway station together. If each requests 1 megawatt, the site could briefly demand 4 megawatts before accounting for conversion losses, cooling equipment, lighting, or other station loads. That is power on the scale of a significant commercial or industrial facility. The local transformer may not support it. The utility connection may not support it. Even when the hardware can deliver the peak, doing so repeatedly may trigger expensive demand charges or require costly grid upgrades. This creates a contradiction. Drivers want chargers that are always available and extraordinarily powerful. Station operators need enough paying customers to recover the cost of equipment that may spend much of the day waiting. A fuel pump stores its energy in liquid beneath the station. Electricity normally has to arrive through the grid at nearly the same moment the vehicle demands it. One possible solution is stationary battery storage. A station can draw power more slowly from the grid, store it locally, then release it rapidly when a vehicle arrives. In effect, a large stationary battery can protect the grid from the violent power spike created by a much smaller charging stop. Solar generation may contribute energy, but it cannot guarantee megawatt output whenever a driver connects. The station still needs storage, a strong grid connection, or both. Another solution is intelligent power sharing. Instead of promising maximum power to every connector simultaneously, the station allocates available power according to each vehicle's condition. A nearly empty preconditioned battery might receive the highest rate. Another vehicle approaching 80% may already be reducing current. A third may be too cold, too hot, or incapable of accepting megawatt charging at all. The station can redirect power second by second, but now the advertised charger rating becomes less useful. A charger labeled 1 megawatt may technically produce that number while one compatible car is connected under ideal conditions. It does not mean every stall can provide 1 megawatt at the same time. It also does not mean the battery will request peak power for the entire session. This is why the charging curve remains decisive. Near the top of the battery, voltage differences between cells become increasingly important. The management system must avoid pushing the strongest cell comfortably while the weakest cell crosses its limit. Charging usually slows as the battery approaches full. CATL's claim of reaching 98% in 6 minutes and 27 seconds is therefore particularly aggressive. But the result will need to survive the conditions that demonstrations cannot completely reproduce. A 10-year-old battery will not behave like a new one. A vehicle parked overnight in extreme cold will not behave like a laboratory-prepared pack. A car towing uphill, then immediately entering a charger, may arrive with a hot battery. A station sharing power during a holiday rush will not behave like an isolated test charger. And drivers do not follow laboratory routines. Some will repeatedly charge to full. Some will arrive with almost no energy remaining. Others will connect without selecting the charger in the navigation system, giving the vehicle no opportunity to prepare the battery. The 6-minute figure is therefore not a universal promise. It is closer to the outer edge of what the complete system may achieve when the battery, vehicle, charger, temperature, software, and grid all cooperate. That limitation does not make the technology unimportant. It reveals where China's deeper advantage may be forming. China already possesses the world's largest public charging network. By the end of 2025, it had more than 4.7 million public charging points, representing over 65% of the global total. Its fast and ultra-fast public charger stock had grown to roughly 2.2 million points. China has also set a goal of reaching 28 million total charging facilities by the end of 2027. Those numbers do not mean millions of Chinese chargers can already deliver 6-minute charging. Most cannot, but they show the scale of the deployment machine surrounding the battery. CATL is not developing in isolation. Chinese battery producers work beside domestic automakers, charging equipment manufacturers, utilities, property developers, fleet operators, and government planners. BYD has already announced production vehicles and charging technology designed around 1 megawatt power, claiming approximately 400 kilometers of added range in 5 minutes. Its newer system pushes the claimed single-connector power even higher. This competition changes the speed of learning. Every compatible vehicle creates charging data. Every station exposes failures. Engineers learn how connectors age, where cables overheat, how drivers behave, when queues form, how batteries arrive thermally unprepared, and which charging profiles preserve life. That information can return to the cell designer, vehicle software team, charger manufacturer, and network operator. A foreign automaker may be able to purchase a fast-charging cell. It cannot purchase years of system-level learning in one transaction. It must integrate the battery into a safe pack, design the cooling circuit, validate crash protection, rewrite charging controls, certify the vehicle, secure compatible chargers, train service technicians, and convince station operators to install expensive equipment. The hidden moat is coordination. Gasoline achieved its advantage through the same kind of coordination. The modern fuel stop feels simple because more than a century of infrastructure hides the complexity. Fuel is refined, transported, stored underground, standardized, pumped rapidly, and sold through an enormous established network. Electric vehicles do not have to copy every part of that system. Most charging may still happen slowly at home while the driver sleeps. That is an advantage gasoline can never offer. Ultra-fast charging is needed for the smaller number of moments when waiting matters most.